Good afternoon, everyone. I hope you are doing great. So without any further delay, let's quickly go through the things that we have covered in the previous sessions. We talked about the scenario that we have limited number of pictures. In that case, CNN gives an acceptable result. Like if you just have 2,000 images of cats and dogs, if you define simply, this is the copy and paste and checking. If you simply create some conv2d max pooling layers, the way that you see here, it gives you, and that is the summary of the layers. And what happened? After this, we said, let's flatten it. And then we said, let's have just one hidden layer. That's densely connected layer. And then this is the output. And we need to have sigmoid because it is just a binary classification. We want to say if it is cat or dog. That is the architecture of our neural net. And then we say, let's have a compile parameters. Everything is explained thoroughly. The only thing is we said we have to use learning rate instead of LR. Still it works, but it gives warning. And then we said for any data pre-processing, we need to go through all these steps like reading a file, converting from JPEG to RGB, and normalizing it and so on. And we said Keras is kind enough to do all those things for us by importing image data generator, scaling down. And this generator, we said it's like a truck that goes from image 1 all the way to the last image, and then it goes back like a loop and starts from the beginning. So we need to have a kind of termination condition. You remember? This is explanation of how generator provides results for us. So what actually we did, we said, let's have a generator because we wanted to have a better result. We said we are going to use augmentation. I'm sorry, give me a second. Yeah, we said we want to have augmentation. And the reason for that is, if I show you here, the idea was, guys, when I start from picture number 1 all the way to the last picture and bring it to the network, for a second, imagine that conv2d and max poolings, what we call them convolutional base and dense layers, they are just consolidated networks. I want to know, when we use augmentation, what actually happens when we go from all these pictures once from the beginning all the way to the end? How many epochs happen? I'm telling you again. Imagine that we go from picture 0, index 0, all the way to 1999. We go through them all and bring them all the way to the end. When we go through all these picture once, how many epochs? How many epochs? So correctly, Huai, did you answer? Oh no, it's not the answer to this. Well, this is one epoch, right? The augmentation idea is, if we have, for instance, 20 epochs, every time you just get a similar picture, but not exact picture, doing some techniques like rotation, flipping, zooming, zoom in, zoom out, something like that. So if you have 20 epochs picture 0, index 0, is going to show in 20 different forms in every single epoch, right? So epoch 1, I have, for instance, zoom in. Epoch 2, I have rotated. Epoch 3, I have zoom out, that version. Is it clear? If yes, please type 2. Thank you, Ivan. Ivan? Okay. So that is why we started applying data augmentation, and we said we could have all these parameters. Erdal in the previous session asked one question, and that was, what if we get exactly similar picture from, for instance, for picture 2, we get exactly similar picture for 2 different epochs? The answer is because we have a huge range of freedom, like we have 40 plus 40 minus 80 degrees here. We have 0 0.0, 0 0.1, 0 0.2. And then we have also a shear range, a zoom range, and so on. The multiplication of all these possibilities provides us a big range, like, for instance, 100,000 possibilities. It is very rare that we can have two consecutive epochs with the same picture. And if that happens, it doesn't matter. It's like you do not apply augmentation. It's not a big deal, right? While it is close to 0, the chance of that. And after that, we just try to show you what could happen if you have one cat picture, what could happen if you apply augmentation. So you see that we have one picture, but we do augmentation, and nearest pixels, that is the last element that we define here. If you see, it says that the fill mode is equal to nearest, so it's not blank. It tries to fill the picture with something reasonable. Imagine we need to have an scalable solution. So definitely you can apply something like Photoshop and so on to modify the picture, but that's not the goal. We just want to have something reasonable that looks like an original picture, so you just fill with the nearest pixels. The part that because of the augmentation, for instance, here we have rotation and we have zooming, or crop. So that is why we have a blank here. After that, we said, okay, apart from augmentation, because actually we do not have 20 different pictures, we have technically one original picture, and we make 20 remix of the original picture. There is a big chance that we have a kind of conspiracy among all those pictures, means that they are very much correlated. The meaning of conspiracy here means that the examples are not very much independent, and that is not something that we expect or we want to have. That is why we go to extreme value for dropout, like 0.5. And if you see the result, combination of augmentation and dropout gives us a very good result. And in some cases, if you see, the training loss and the validation loss are pretty close. We do not have that much vivid overfitting. Then we said, and from here, I start a new topic. We covered part of it in the previous session. So we said, how about using a model that we have trained that model over a vast number of pictures. That is what we call it using a pre-trained convnet. So that pre-trained network, it could be something like ImageNet that contains 1.4 million labeled images over, and it has 1,000 different species, like lions, cats, lots of different categories. Many people have used different architectures over and made models using ImageNet. One of the most famous one by Simonian and Zisserman, if I'm correct in pronouncing. They provided something that they called it VGG16, and considering the conv2D and densely connected layers, we have 16 layers. If you just search for that, Google it, you can see some images that they show you why they called it VGG16. And we have other samples apart from it. And we said that let's have a feature extraction. And then we said that this is super important. ConvNet's use for image classification comprise two parts. Starts with a series of pooling, means max pooling, and conv2D layers, convolution layers. And we have the densely connected layers after that. But the convolutional part, the convolutional base part, is what is more generic, right? So that is why we are going to use that part. If you remember, we used this part. We said, okay, let's get the VGG16 means that architecture using the ImageNet. So it is going to borrow the weights and biases of the ImageNet and bring them all to the architecture that we have. And when it says that include top false, which part it is not going to, it's not going to include? Anyone can tell? I repeat the question. When we say include top is equal to false, which part we are not going to include? The convolutional part or the densely connected part? Okay. Which part is more general, Parsa? Which part is going to give you more general stuff? Means curves, horizontal lines, filters for horizontal lines, vertical lines. Which part gives you more details, more general things? Okay. Guys, the thing is, if you look at these parts, like convolutions, let me just show you one thing. If you say, I want to have a conv base and include top equal to false, look at the result. We are going to have all those convolutional parts, right? And we do not have any dense layers. Why? Because the conv2D parts, these convolutional parts, they provide filters for us already trained based on 1.4 million pictures. So we have good reusable filters. That is why we are going to use this one. but we are going to ignore the dense layer, means those hidden layers come after, those hidden layers that they come after convolution. Long story short, if I get back to this question, when we say include top equal to false, means ignore the densely connected layers. Okay, so after that, this was a challenging part. I asked people to find how this algorithm works. It was not the easiest, but we just said here, I quickly just recap. We just used the data gen equal to image data generator dividing by 255 to normalize it. One question that we can answer easily, we do not have train data generator and test data generator, means that we do not have augmentation parameters for this approach. In other words, if you just extract the features, it means like this approach, approach A, means you have all those pictures, you just bring them into conv2d once, and you're going to have filtered result. Here, it should be filtered results. So I was lazy, I just said filters. Means that those kind of strings we have, which had 8,192 pixels, we have those 8,000, we just apply these conv2d once and we get to the result. Does that make sense? This is the most expensive part. So we just bring everything once inside this tunnel, and we have those strings, 8,192 pixels. And then we use densely connected layers and bring them. This time we are going to use, for instance, 20 epochs, 30 epochs, 100 epochs. This is not a very cumbersome process, this part, densely layers. But the problem is you cannot have end-to-end, and you cannot use augmentation techniques because you just go through the conv2d once. This is the first approach that we talked. But the second approach is, as you see, well, let's just consider, you see that we have quite good results here, almost 90% accuracy, almost, for the for this feature extraction type A. But the thing is, we cannot get any better unless that we use data augmentation. If you use data augmentation, actually, the algorithm is way easier, but the time that it takes is huge. So look at this one. We say, let's have model sequential. We add conv base model to the model, and then we add this flattening and then hidden layer. This is the compressed way of showing everything that is inside VGG16. That provides you 14,713,688 parameters. If you go back to VGG16, you see that the last layer, it shows that, yes, we have this amount of parameters. So we can consider all of these parts, means this. as just one layer that contains all those conv to these max poolings and so on, and provides 14 million some hundred thousands, right? Okay. Then if we say now use that, there is one big problem. If we do not say anything, it is possible when you start with a new data set like cats and dogs, instead of 1.4 million images that we have in ImageNet, then because the values that we have for weights and biases here are random, they show a huge loss at the beginning. So what's going to happen? It is going to propagate all those problems to the previous layers, and it is going to modify all conv to the max pooling layers that we had before. The result of that would destroying the pre-trained network. That is not what we want. We want to use those pre-trained network values. So what can we do? We can say that, hey, make conv base means those VGG layers. Not trainable means do not change them. If you see before saying that we have 30 different layers that we can train, but after saying change the conv base, trainable equal to false, means this layer equal to false, this layer, then we only have 4 trainable layers. And you might say, Reza, we have only 2 layers. Why it shows 4? Because we have weight and biases. We have weight and biases. So weights and biases. So it's going to be 2 weights, 2 biases. That is why it shows 4. And now it's the time that you can apply the augmentation, because you go end to end. You go from here all the way to the end, right? So every time that you see picture 00 in a new epoch, you apply augmentation. So it's going to be a remix of the original. And next epoch, the same. Next epoch, the same. Vividly, it is going to consume way more time, something like 10 times at least. So in that case, if you go through all these steps, you're going to see you get to something like 96% accuracy, and it is way above what we had just by using augmentation, or just by using feature extraction without including the augmentation. I want to just show you one thing. So flattening and yeah, densely connected layer. Give me a second if I can. So again, here, look for the train data generator. We have the augmentation, but for the test that we are going to use it for validation, we don't have any data augmentation. We shouldn't touch the data that we have. They are supposed to be untouched and unseen. And this is, again, I have changed this one to learning rate. And this is what you see as the result. Everybody, if you please go to, let me just give you the file as well. Final package. Okay, they are 150. Okay. So you have the file, please download that. And then drag and drop to Colab. If you go down here, the funny thing is comparing the last two graphs with the second last two graphs. You see, in these second last two graphs, the training works better, and we have quite reasonable overfitting, like 6-7%. But the funny thing here is when you combine feature extraction and augmentation, for the first time, you see that the validation result is better than the data in hand. So we have underfitting. Okay. So my question for you is why we could have underfitting in such cases? To answer this, please take a look at 153. These are the convolutional base that are connected, base layers that are connected to densely connected layers. Anyone can step in and express their opinion. While you try to guess or type. Okay. Can you see these filters? If yes, please type 1. Okay, awesome. Guys, do you see that these filters are very general? They are like taking some horizontal lines. If you apply this on any picture, this is going to grab diagonal. This is going to grab horizontal, right? Some dots, some patterns. If we go a little bit higher, it's going to be a little bit more sophisticated in the next layer. And if I go a little bit, guys, can you admit that in block 2, we have more sophisticated layers, filters? And if I keep going, do you see that we have still, we are in block 3, not very much high in VGG. And if I keep going, it's going to make complex and more complex and more complex. So among all those, if you please confirm by saying it is true or false, type T or F. Can we say the first block, which contains those simple filters, they are more general? You can find more examples that if you pass some pictures through those filters, you can have some results out of it. True or false? Awesome. So these are more general filters. Here we have a little bit in block 2, a little bit more sophisticated, more complex filters. The chance that not 100% of the pictures could get through is higher. True, false? Lovely. So the more that I go higher, when I get to block 5, can we guess it should be way more specific type of filters, the result of combining all those previous filters to just make it, tailor it to the data set that I have. So if I keep that, there is a big chance that I cannot use all those filters properly. True, false? To answer that, look at the result that we have here. Let me just bring it faster. Imagine that I start having, this is the first conv 2D. Guys, do I have any empty cell here, any empty picture? No, because they are very basic. The higher that I go, the more hollow, the more empty. So look at the last layer. I repeat my question, true or false? If I go higher and still I emphasize, I keep the conv 2D in the fifth layer, there is a big chance that I have filters that no picture can go through and get appropriate results. True or false? Okay, awesome. So you see that, what if I can tune this part? What if I say that, you know what, unfreeze? You remember in the previous approach, we have frozen all the layers. What if I say, you know what, for the last block, just forget it. Do not freeze the last layer and apply everything. Look at this one. Okay, if I say, show me the summary of the network, it's going to show you exactly what we had. But here I'm going to say, turn it back to trainable. If, and set trainable equal to false. I say for layer in conv base layers, if it is block 5 underscore conv 1, set the trainable equal to true. Guys, we set it everything to false, right? If the set trainable, let me just show you in this example. Please call up, bring okay, please bring that to our collab. It's way easier to explain it on the code that I have. Oh, my apologies. It's the previous one that we already had. It's in. Okay. Look at this one. Here I said conv base, guys, this is in the one that I have already shared with you, 142 to 152. I said conv base dot trainable is equal to false, means do not touch that part. So this is what we showed you, that before it was 30, and after that it is 4. I explained that part, and using all those augmentation and so on, it gives us the result that you see here, right? And why I cannot find what I did. My apologies. When you have lots of codes, that could happen like this. Okay, I just explained it here. Hopefully I'm gonna find it. What we actually do here, we say, hey, make everything in the network trainable, so it is not frozen anymore. And then we say, except for the layers that the block 5 conv1 is the name of the layer, set everything else equal to false. My apologies that I confused you in here. Look at this name, block 5 underscore conv1. And if I show you the name of the things that we have, it's exactly block 5 conv1. That is what I corrected in my code. I was hopeful to find the things. We need to add more blocks, like say block 5 conv2 as well, block 5 conv3 as well. In that case, you convert all of these parts trainable, while you keep the block 1 all the way to block 4 frozen. I repeat that. You are going to keep all block 1s all the way to end of block 4 frozen. And the only thing that you are gonna you're gonna make it trainable is block 5. So I have a complete version of this code. Tomorrow in the lab, I'm gonna show you this one, the corrected version of this one. And then what you do actually, you're gonna say, now with this new architecture, just go through all the pictures from picture number index 0 all the way to 1999. And for the first time, what we are going to achieve is going to be something close to 97%. And the funny thing is, this is better than the results that they got in 2013 using 25,000 pictures. So tomorrow, the fine-tuning is the part that we all are gonna work on. Would you please go to the quiz? So don't worry about this part that I couldn't find it here. Tomorrow we are gonna go through it in the lab. Would you please go to the quiz and confirm if you can see the quiz number 11, last quiz? Okay, that's a good question. Stefan, I'm going to answer that. Would you please first confirm if you can see the quiz and you can start, you're able to start the quiz? If yes, please type Y. Okay, awesome. And the question that Stefan asked, I'm going to share it on the screen for people who watch this later. He asked that on page B, which contains all the tutorial videos, are they all acceptable for doing for the assignment or just the 5-hour tutorial? I can even enhance the possibilities. They are just suggestions. Means that you can pick any of them. They are equally acceptable and valuable. And apart from them, if you find something more interesting for you that you want to use it later as a part of your resume, feel free to choose any other topics. But because I had some samples that people just brought like 10 lines of code, considering that as the final project, I provided some criteria like having 50 lines of code, having at least a few graphs and so on, not to say that, okay, 10 lines of code, apple and orange, deep learning project done. That is the only concern. So at least we spend a few hours on that, learning something, enjoying something, and just recording what we learned. Did I answer your question, Stefan? Okay, my pleasure. Thank you very much. I'm going to, sir, can I ask about my idea for assignment for after everyone has left? Yes, I'm going to stop recording. Thank you very much. So see you in the lab, online or in person.